Okay, this is Logistic Regression lecture number 1, or workshop session number 1. I've already missed 10 minutes of me talking without recording. Okay, right, so here again we're looking at the example of, is the candidate going to win the election, yes or no? And the variables can be anything. Here we've got the amount of money they spent on the campaign, was the campaign negative or positive? Are they the incumbent? Are they currently in office? Are they male? Are they white? Are they educated at a certain level? Anything goes. We like it if these variables are also dichotomous, like male-female, like incumbent, non-incumbent, that kind of stuff. But it doesn't have to be. Very often they're continuous variables like age. Very often they're categorical, like education. Now, categorical variables have a special problem that we're going to find out about later. The categorical variables like education, maybe got a PhD, master's, bachelor's, or something like that. So, and they don't have any, that's a bad example. Let's say we're doing province of birth. So Ontario, BC, Quebec, let's say, three provinces. There's no way to rank them, they're equal value. And so province is one of these explanatory variables that is very different from the rest of them. And we're going to look at these separately when it comes to logistic regression. We don't like for them to be there, but they're always there. And so we have to look at them especially. Okay, so this is the outcome, win or lose the election, and this is all the stuff that's going to explain that outcome. Okay, so our research question is always something like, what are the factors associated with blah? It's never what causes blah or what predicts blah. It's always what's associated with because all we know is in last year's data, because we haven't got future data, we've got previous data, all this stuff, when mixed together, is mathematically, has a relationship with this outcome. We don't know if it's causal. It's all just associations. So we have to be careful with the language we use. So in this case, what are the factors associated with winning an election? Okay, with whether a political candidate wins this election. So why do we care? We care because it allows us to figure out, among all the super variables, which ones are the most pertinent in explaining whether or not he wins the election, but also how much it is pertinent. Because we're going to be able to say which ones really count and how much they count. Those two things put together make it valuable. So how to do that? Well, the p-value, you've all seen p-values before, I hope. If not, we can take a little detour and talk about p-values. So the p-value for each of these variables relationship tells us whether or not it matters. And we're going to be able to compute an odds ratio, and I'll go over what that is in a second, about how much this thing predicts or is associated with whether or not he wins the election. So we'll spend some time on p-values later on, but in general, the rule of thumb for p-values is if it's low, the null must go. You heard that before? In other words, if the p-value is low, that means it's good. That means it means something. That means we want to keep that variable. It's really important. What does low mean? There are no rules, but we tend to use guidelines of less than 0.05. We prefer to use guidelines of less than 0.01, but anything above 0.05, it's probably not that relevant, right? So you want a low p, and I'm using the word factor here. Factor is any one of these variables that we're trying to model against our outcome. Right? Now stop me if at any point you lose me. I lose you, okay? So, and then we're going to compute an odds ratio. All right. This is what we're going to create. That's intimidating, I know. But you're not going to see this ever. Keep in mind that that's what in your mind with computers trying to create. Right? So what's the outcome? The outcome is he going to be elected or not? But that's not what that is it? That's something else. This is actually the natural logarithm of the likelihood of the outcome. Do you remember natural logarithms in math? There's log base 10, log base 20. Log base e is a natural logarithm, right? P here is the probability of the outcome. So the probability that our guy gets elected divided by the probability that he doesn't get elected and is the likelihood, and the natural logarithm of that is our outcome. This is called something very special. So it's called a logit. That's where the name comes from, Logistic logit. So the logit is this relationship here. If I can plot, as the probability of the outcome increases, this is what the logit looks like. If I were to plot the logit, which probability looks like this, it's not really relevant for what you're going to do. Just recognize that there's a lot of math underlying this, and this is what it looks like. So let me go back for a second. So it means that each of these coefficients here is in fact the natural logarithm of something. It is a natural logarithm of an odds ratio between each of these and the outcome. Right? Let's go over that a second. So once we create this equation, each of these coefficients here are put in front of each of our variables. I'm going to use the word variable and risk factor interchangeably. So when it's a risk factor, it's predictive. It's something that has a relationship with the outcome. So smoking is a risk factor for lung cancer. In this case, being an incumbent is a risk factor for being elected. Having lots of money is a risk factor for being elected, and so forth. How much is it a risk factor? This much. What is that? That's the natural logarithm of the odds ratio. That's kind of critical, because at the end of all this, you're going to be able to say, I know your study is about HIV positive outcome and certain criteria, people say that in the presence of these other factors, if one of my subjects is older, the odds ratio for her being HIV positive is this. That's a wonderful finding. Okay? So that's the power of this. It allows us to figure out, in the presence of these other factors, what is the meaning of this relationship. Okay? So let's go over what an odds ratio is, in case you've never covered this before. Have you seen odds ratios before?
Okay, yeah, I'm looking at my course syllabus from the one I took. We did simple linear regression models, multiple regression analysis, including variable selection techniques, regression diagnostics, goodness of fit test, nonlinear regression.
Nonlinear regression. How was that? Okay, that's fine. That's fine. This sounds like you covered a lot of interesting things.
Yeah,
that's good.
Yeah.
That's fantastic. All right, so you've got some kind of background that's probably beyond the rest of the students, which is nice. Especially the diagnostic stuff, which is good. Okay, so but you did odds ratios. Mm-hmm. I know we should have in our program. Did you do odds ratios? Okay, good. That's good. So it's new for somebody. So an odds ratio is a way of quantifying a relationship between two dichotomous variables. In this case, let's say, again, do you get elected, do you not get elected? That's our dichotomous outcome. And this is the risk factor. Is he an incumbent, is he not an incumbent? I can do this for every one of my risk factors. Incumbent, non-incumbent, male, female, old, young, whatever it might be. Only if it's a binary risk factor, dichotomous risk factor. If it's not a dichotomous risk factor, the computer does some fancy things to estimate the odds ratio. I'm going to show you, in principle, what an odds ratio is using this dichotomous example. So let's say I got 106 people in my data set. And I'm only going to examine this one variable right now. And so of my 106, 69 get elected, 37 don't get elected. 60 are incumbents, and 46 are not incumbents. And this is the way their relationship splays out. So this is, out of my data, I can just pull that in. So 45 people got elected and they were incumbents, and 24 got elected and were not incumbents. Okay. A probability would be this divided by that. So the probability that if you're an incumbent, you get elected, 45 out of 60, right? What's the probability that you're not incumbent and you got elected? Be 24 divided by 46. In other words, out of all the people who are not incumbents, how many got elected? 24. Pretty straightforward. Probability we understand. Odds is harder. Odds is the probability of something happening divided by the probability of it not happening. Okay?
If it's happening divided by it's not happening.
Exactly. For example, what's the probability of one of the students in this class being male? There's 3 of you, there's 1 male, so probability is 1/3. The odds would be 1/3 divided by 2/3.
Oh.
In other words, half, 1/2. So the odds are 1 and 2. So 1 male, 2 females. That's the odds. So the odds of the incumbent getting elected is 45 divided by 60 divided by 15 divided by 60. That gives me 3. That's the odds of the incumbent getting elected. Now, the odds of someone who's not the incumbent getting elected would be 24 divided by 46, divided by 22 divided by 46, 1.09. Okay? So, even if you're not the incumbent, you've got a positive odds of getting elected. However, if I compare these two, I find that this one is 2.75 times greater than that one. So that's the odds ratio, the ratio of these odds to those odds, right?
The ratio of which to which?
Of this odds to those odds. So it's
Okay.
There's a short form to compute this, and the short form is that times that divided by that times that. So cross products. That divided by that divided by that. Okay. So that gives us 2.7. What does that mean? That means that if you're the incumbent, you've got 2.75 greater odds of being elected. That's very encouraging. It means that incumbency, probably an important variable in our study, right? So why do we care about odds ratio? It's an estimate of the relative risk. Relative risk is ultimately what we care about. What is the risk of being elected if I'm the incumbent? What is the risk of getting lung cancer if I'm a smoker? What is the risk of being pregnant if I'm unprotected sex? It might be. It's relative risk. Very often, though, the data sets are arranged such that we cannot compute relative risks. Don't ask why. It has to do with the nature of the design. A case control retrospective design doesn't allow relative risk calculations. If you don't know what that is, don't worry about it. And so odds ratio is used to estimate a relative risk. Yes?
Meaning of the general population, not just in a sample. Or
Well,
still in a sample.
we're still in the sample. However, at the end of the day, the sample is used to generalize about the general population. So this technique says nothing about how your sample is generated. Is it a representative sample, for example? Do not. The computer doesn't know. All the computer knows is I can do this math to figure out what's happening in here. So this is where the human component comes in. Was the design robust enough to say that we can extrapolate and generalize? Okay, good question. In other words, so it tells us the risk of getting the outcome if the risk factor is present. So if incumbency is present, what is the risk of getting elected? 2.75 is our risk, which is pretty high. Rule of thumb is anything over 1.5 is pretty high. Right? If it's like less than if it's less than 1, then it's a protective risk. So let's say I'm looking at the outcome of getting Parkinson's, yes or no, and the risk factor is smoking, and I get an odds ratio of 0.5. What does that mean? It means if I smoke, I have a lesser chance of getting Parkinson's than if I don't smoke. That's true. Smoking is protective against Parkinson's disease. Yeah. Right. So 1 is the magic number. In odds ratios, 1 means nothing's happening because we're dividing two things. If we divide two things, 1 cancels them out. So anything that's not 1 means something. So the bigger than 1 it is, the more likely the risk factor is associated with the outcome. The much less than 1 it is, that's the right way of phrasing that sentence, the much less than 1 it is, it means the greater the chance the risk factor is associated with not getting the outcome. The closer it is to 1, the more likely it is that risk factor has no influence whatsoever. Now, how do we know? Let's say it's 1.09, or let's say it's 0.99. Is that close to 1? It is, but does that mean it's not worth anything? What's the cutoff? How do we know that? Any idea? That's where the p-value comes in. So the p-value is going to tell us whether or not that odds ratio means anything. Okay? So we're getting pretty ahead of ourselves, but because I want you to see where we're going to end up, and then we're going to get there later. Okay. At the end of the day, what we care about is p-values and odds ratios. So what does the regression give us? It gives us the odds ratio of each factor in the presence of the other factors. So I just showed you, by hand calculations alone, I can compute the odds ratio of incumbency and whether or not you get elected. Isn't my job done then? I showed you if you're incumbent, you're 2.75 times more likely to get elected. No, because let's say if I'm a man, I'm 2.5 times greater to be an incumbent. Maybe it's the fact that I'm a man that's getting me elected and has nothing to do with the incumbency. Right? Or maybe if I'm rich, I have a greater chance of being the incumbent and getting elected. So maybe it has nothing to do with incumbency, it has everything to do with being rich. We don't know. That's why we have all these other variables thrown in. That's why we build an entire regression model so that the presence of all these variables controls the other ones. Just now, I only did it for one variable, for incumbency. If I throw in money, that's going to change the relationship. Suddenly, I guarantee that relationship will come down. It won't be 2.75. The question is, how much will it come down? Will it come down to the point where it has no influence whatsoever? It might. In fact, it often does. So when we build a regression model, we're looking for all the right variables so that in the presence of each other, we get something resembling truth. Now, you and I talked earlier about which variables to throw in. Well, that's where the intellect comes in. You have to figure out what your question is and what your field is to figure out, well, this is relevant, that's not relevant. The statisticians, and I'll say this as a statistician, we're just trained monkeys. Just give us numbers and numbers, you go, right? We haven't got the insight to say, well, that's not relevant, that's not relevant. What the statistician wants to do, what the computer wants to do, is to put absolutely every variable they can think of into that model and account for everything. Because why not? The reason why not, do you know what the reason why not is? Why not we throw, if I throw in his sex, how much money he has, whether he's an incumbent, his shoe size, how many siblings he's got, his grades in high school, I can get all that information. I can make an enormous model. Why do I do that?
Maybe they interact, like shoe size.
They interact. We can control for that, though. Okay. I'll do that later on. I do that. The reason, quite simple, a couple reasons. One is, if you have too many of them, the system kind of falls apart. But also, that it's possible with enough data to fit a perfect regression that has no bearing on real life. Ultimately, we want something that's useful and resembles real life. As an example, let's say I have here some points, and I say let's plot a straight line through this. Remember linear regression from stats class, right? I can say, well, that's a pretty good straight line, right? It's pretty close to all those. That's a good estimate of that relationship. I can do what's called a Fourier analysis or a power series analysis and actually make a line that goes through all of this. It'd be something like, y equals x sine theta squared plus tan, blah, blah, blah. It would look completely arcane and meaningless to you, but I can totally do that. Find a curve that goes through each of them. But who cares? This does not resemble real life. So let's say this is distance and time, and this is my car traveling down the road, and I'm using this to figure out my acceleration. That's going to be, my velocity rather, right? So I've got all these points, I'm measuring different points of my thing, I'm plotting a line, and the slope is going to be my velocity. That has no bearing on this. I can't predict a velocity based upon that curved line. So this complicated equation here is not useful to me. By the same token, if I throw everything I know about these politicians in here, it doesn't represent the real world. At the end of the day, my research question has to do with which of these functional factors are predictive or associated with having HIV status, getting knocked out, and I forgot what your study is. Birth weight, right? Birthweight.com. Is yours logistic as well, or is it?
Yeah. Okay,
good. Okay, hope we're not going multiple. Sorry. Okay. Okay. Right. So it's a long way of saying, in the real world, we care about a relationship that makes sense. Also, with every variable you add, you're getting tiny, tiny incremental improvements in the fit, to the point where you don't even see any improvements anymore. So why have so many? So we just get it down to a set number that makes some kind of sense. Okay. Whew, so okay. So why is this important? We have to talk about more terminology here. Adjusted and unadjusted. So when we just did that relationship just now between the incumbency and whether or not he gets elected, that was one risk factor, right? And I can say that, I can go on TV tomorrow and say the incumbents have a 2.75 chance greater than non-incumbents getting elected. And that would be a big deal, and the pundits would talk to me, and that would be all kinds of stuff, right? But that's not in the presence of other variables. When it's not in the presence of other variables, we say it's unadjusted. When it's in the presence of other variables, we say it's adjusted. We're going to use that term a lot, right? Because we're going to compare the unadjusted and adjusted to see how much it changed. Let's say unadjusted is 2.75. We just saw that. Let's say when I throw in am I male, it goes down to 1.4. So suddenly that change, the adjusted to unadjusted to adjusted change, is huge, and that's interesting. It means that everything we thought we knew about the power of incumbency is actually not true. A lot of it has to do with being male. So you see how the narrative starts to unfold now. Right? So at the end of the day, yes, we care about the odds ratios, we care about the p-values, we care about the changes. And that's going to tell the story that comes out of your thesis, because your thesis is about writing a story. Okay. So regression allows us to combine a variety of risk factors into a single equation in the presence of other variables. Right. So in your thesis, you're going to create something resembling this table. So I just made these numbers up. These are the numbers. So let's say we're still doing our example of whether or not you get elected versus not elected. And these are some of the variables that we care about, some of the risk factors we care about. This is the unadjusted relationship between each of these and our outcome. So let's say I do, like the odds ratio I just showed you, between are you incumbent and do you get elected. And let's say I use the computer and I got a p-value. That's the p-value. That's pretty low. That means that's significant, right? And how much money they spend. Let's say I do, and also I do a 0.045. Here are all the p-values of the individual relationships of each of these variables with the outcome. That, in and of itself, would probably get a paper, but it's not a thesis, it's a paper. Now, when I run the regression model, and I take those b's, those betas, beta sub 1, and I take the natural logarithm, and I figure out the odds ratios, and I figure out the p-values, all of them, these are the p-values for each of those relationships. Now, this one didn't change. So the incumbency is still relevant, even in the presence of all this other stuff. Therefore, incumbency, well, that's definitely something that's going to be used to predict whether or not you get elected. This one went from being vaguely significant to not significant at all. So the amount of money you spent, actually we thought was important, it's not really important. It's probably explained by these other factors here that are masking this. Are you male? Well, it wasn't important. We did it by itself. Suddenly it became important. Or the age. The age was not important, and it is important after you control, and so forth. So at the end of your thesis, you're going to go through each of these and see, did they change? You'll find that things you thought were significant ends up not to be significant. You tend to find fewer things that are significant after you control for them, because that's the way the world works. Right? Yes?
I have a question. Does this take into account, say, if the candidate is male, he's more likely to be incumbent?
It does not.
Okay.
So you're talking about their confounding and interaction terms.
Right. Yeah.
We'll get to that in the future sessions. That's an entire day's work. Right. Totally right. Yeah. Good for having that way of thinking. Right. So that's one of the pitfalls of this approach is people who do it naively, just SPSS run it. SPSS can't determine which ones are confounders. There's a process we go through which is time-consuming and laborious to identify which ones are probably confounding. And we'll define what confounding is later if you forget. So, how do we do this? We have software. If you haven't got SPSS, wink, 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 don't share this, go to my illegal download site. Download the evaluation copy, which in fact is not the evaluation copy, it's the cracked copy that never expires. But screw these guys who want your money. I say, just don't tell them I sent you there. So that's where I store it all. It says evaluation, it's not evaluation, it's the real deal. It's going to follow the instructions we install. All right. You guys already know about that. If you don't, then there it is. Okay. How are we going to go through all this? Well, in the next couple of weeks, we're going to go through how to understand our data. It's critical to go through our data set and to understand each of these variables, means, how they're distributed, and so forth. We're going to explore all the variables. We have to determine which ones are what type. We'll look at that in a second. You have to recode a lot of them. So recoding is a big part of this. By recoding, I mean maybe you have education in 4 categories, and only one guy's got a PhD. Well, he's not very useful, that one guy. You have to recode him as maybe combine master's and PhD together. Or maybe you find out that your age distribution It's like everyone is under 35 and 5 guys are over 60. It's a big gap in the middle. How are you going to deal with that? You may have to define average age or have an age cutoff instead. All these things you have to think about when you look at your data. You have to remove, you're guaranteed to have to remove some variables. No question, some will have to go. Because some you'll find are redundant. Like age and age group, they're the same thing. Or BMI and weight. Well, one of them contains the other one, so we have to decide which one you're going to keep. Right? We have to impute new variables. What does that mean? Well, like I said, let's say you have education, PhD, master's, bachelor's, and high school, and we're going to create a new variable that just says high school and above. So this becomes 4 levels, becomes 2 levels. That's imputation, we call that. SPSS has the recode variable function and does it for you. So that's kind of fun. Again, identifying confounders interaction. That's going to be an ordeal. And then, only then do we run the body logistic function. Only then do you press that button. And there are many ways of doing this, and I'll give you a preview of what these ways look like. And I struggle with whether or not to tell you about this stuff, or whether or not to let you do it the most simplest way. There's one called forward elimination, there's one called backwards elimination, and there's one called forward entry, backward entry. That sounds dirty, I know, just put that in your mind. And then there's and what that means is, the forward elimination is this, is we have, I was confused these. Forward elimination is, you have your list of variables, you see how well they fit, then the computer will take out one of them, see how well they fit, put it back in, take out the second one, see how well it fits, and so forth. It'll go through many iterations. You can set the number of iterations, usually at default is 20. Or it can go to the very end of the process, makes the model, take out one, backward elimination, look at it, see how well it fits, take out another one, and pare it down until it fails. I personally like backward elimination, but really for what your project's doing, it really shouldn't matter. So we'll just put that in your mind for now, and to recognize there are many ways the computer can use for doing this, and when you try an SPSS, it'll give you those options. Play with them. Always play. Play, play, play. That's the best way to learn about this. All right. Moving along. All right. So the first thing we're going to look at is frequency analysis of how to do this for understanding your variables. A frequency analysis is just really looking to see how your data is distributed. How many of this occurs here? For example, if you're looking at sex as your variable, how many are women, how many are men? That's a frequency analysis. If you look at age, how many are these ages, you probably prefer to look at a histogram. Right? So you really have to have a feel of what your data is showing. Because if you discover they're all men, you got one woman, well, that's a problem. If you discover that you're dealing with a pregnancy study and you have no women, well, that's a huge problem, right? I know Peter's dealing with mixed martial artists. If they're all over 40, then that's a big problem in our data set. So all these things are important to figure out. So the next few weeks, again, I'm not sure how many, we're going to define variables, recode variables, measure skewness and outliers, and then run the univariate bivariate analyses, do the confounding tests, and then start the process of learning the regression. I don't think we're going to do sample size calculation. We just assume that you have enough. Because if you don't, it's a little too late. So the examiners require sample size calculation. There are wink, wink ways of doing it. Go online to a calculator and just plug in things. And, oh, look, I got plenty. Because that ate up like 6 months of my life doing for my PhD. Sample size calculation. It can be an ordeal. Right. So because this is an unofficial workshop / class, there's no Blackboard Vista for this. So just go to our website, tnr.com. If you click on the academia link at the top, and there's a section now for this, and that's where I'll keep the slides for download. And I just store them on Google Drive, and you get them. I think you got this one already, right? That's plugged from Google Drive. And I'm going to upload a sample data set later this afternoon, and you can get that and play with it as well if you haven't got it already. Again, only Elena gets marked. She's not here, so the rest of you are here voluntarily. Right, okay, so let's begin. There are 2 flavors of variables. You can see that, right? No problem? Okay, continuous and categorical. Very basic stuff, I know, gotta make sure we understand this though. Okay, continuous variables are things like age, height, they're things for which variables flow like a fluid. There's a value in between the numbers. I'm 47 years old, maybe I'm 47 in one day, 47 one day, an hour, 47 one day, an hour and 6 minutes. All that stuff has meaning. So I can parse out my age down to the microsecond. That's what continuous means. That the individual numbers are illusionary and stuff in between has meaning. As opposed to categorical or discrete data, that in which stuff in between has no meaning. Okay? For example, age group. You can be 0 to 18 or just over 18 and 19. It's two different age groups. In between that doesn't have any meaning because there's nothing in between. They're touching precisely. Or gender. Let's pretend there's no such thing as transgender. Let's say there's male and female. There's nothing in between. That kind of stuff. Okay? Now, we like to have dichotomous variables. Dichotomous means having two levels, right? E.g. sex, assuming no transgender, male, female. We dichotomize by turning a continuous variable into a dichotomous variable. For example, age under 40 over 39. So I had a continuous age variable, now I've got two variables. I can trichotomize and quattro-quatomize, I guess. We never did. Always dichotomize. Okay? So we have these levels of measurement as well. You've heard these terms before? Okay, good. So nominal is the most problematic measurement level, and you're going to have to deal with that. It's actually kind of fun, to be honest. So nominal variables, the nom means name. So it's like the province of your birth, or your blood type, or something like that. So categories that you can't rank and you can't do math on. What's the average province of birth in this room? No such thing. You can't do that. So we have to deal with that in a different way. Very, very common problem. Or, I mean, education level, you can pretend that PhD is higher than a master is higher than a thing, right? So that's a different way of looking at it. But we tell it that way. Ordinal would be the case of something with order, like your education level, or the number of rooms in your house. 3 is bigger than 2, which is bigger than 1, but you haven't got 1.5 rooms, regardless of what the real estate agent says. That 0.5 bathroom is a room, right? Interval and ratio, same thing. These are the standard continuous variables. The subtle difference here is that one of them has a real zero, the other one has an artificial zero. So ratio has a real zero, like degrees Kelvin has a real zero, it's absolute zero. Degrees Celsius is interval, it's made up by people, it has no actual meaning in degrees Celsius. So. Or height in centimeters has a real zero. Zero height means something. Okay. Yeah, we talked about that already. So nominal measurement, sex is a good one for nominal measurement. We can code it in terms of numbers. 0 is male, 1 is female, and so forth. It doesn't matter what the codes are, just as long as you have it straight in your head. When you're using SPSS, I highly advise you, in the variable view, to take advantage of the labeling. Otherwise, you'll get really confused fast. So the labels are great, because when you label them correctly or appropriately, when it does analyses, the output will also have those labels attached. So you forget, oh look, my outcome has greater % 0 than, what are the 0 ones? Which one's male, which one's female? I don't remember, but it'll do it for you if you pre-code it. Okay, ordinal measurement, we talked about that. Right, so 1.7 means nothing, interval, we talked about that. Okay, keep in mind, when we move up that ranking from ratio to interval to ordinal to nominal, we lose power, we lose nuance, we lose ability. So, in my opinion, dichotomize at your peril. So if you've got age as a number, like in my sample, I've got women's ages in years, that's great. If I'm going to convert that to age group, have a good reason for that, because we've lost nuance when we do that. Always prefer to have a continuous variable if it exists already. Okay. Sometimes, and I'll show you sometimes why we would choose to do so, but we need to have a reason. Otherwise, we've lost a lot of mathematical power. Okay. Here's a summary of what those things mean. Right. So we assume, and the technique assumes, that your continuous variables are normally distributed. The one thing Sukkot always talked about all the time was normal distribution, right? So you know what that's all about.
Pretty much all of it.
Yeah. Just crazy stats probably have for a long time. And the reason for that is all human characteristics with enough sample pretty much are normally distributed. I can talk forever about the history of normal distribution. Ask Otsuko. It's a fascinating history. And so the techniques that the regression analysis depends upon assumes that your data is derived from normal distribution. So when you go look at your data, investigate whether or not it's normal. If it's extremely skewed, that's usually okay, but not this really, really, really skewed. Right? So you may find that your data has a bimodal distribution, or multimodal. An example of this is TB testing. So you've heard of TB test, anybody? Yeah, okay, right. So they put the thing on your arm, right, and they look to see if there's a reaction. It's called an induration. And they measure that induration, that width of it, to see if it falls within the range of a positive TB test. Do you know how they know how big to look at it?
How big?
Well, they look for I think it's a 2 centimeter. It's pretty big. 1 centimeter. 1.5 centimeter induration. That's because they looked at an entire population distribution of induration reactions. Some of them are just allergic reactions. Some of them are positive TB reactions. The allergic reactions are slightly smaller than positive TB reactions. So what they found at a population level was, if this is the number of people, and this is the width of the induration reaction, most people had 0, a lot of people had 0, but then a small number had, a large number rather, had this size of induration, and another number had that size of induration. That size is bigger, this is smaller. This is the number of people, this is size, right? And they figured out this is the allergic response, that's the TB response. And they put the cutoff here, and that cutoff is 1.5 centimeters right there. Nothing to do with the science of induration, has everything to do with the distribution in the population. Okay? So this is an example where let's say you've got induration data in your data set. It's continuous in centimeters or something. You can model it continuously, but it's probably advisable to look at the bimodal distribution and realize I can dichotomize it here. I can convert my continuous variable to a dichotomous variable with some strong degree of confidence in doing so. Otherwise, I will lose the stuff I'm looking for, which is a TB reaction, in a sea of allergic response. So in the case of, trying to think of your data, how it's relevant here. We've got the time of the fight, duration of the fight. We may find that a bunch of people are knocked out in the first round, and a bunch of people knocked out in the 5th round, and nobody gets knocked out in between. So we can use the round of knockout as being a continuous variable, or ordinal in this case, or we can separate it out and say all we care about is 5 and 1, depending upon how it's distributed. Right? Okay. Oh, look at it. Induration. Wow. You realize that it's 1.5 centimeters. Okay. That's actually a friend of mine in Fourier. That's her induration reaction. That's the actual data of induration in USA. So a large number of people have this. Okay. Understanding data, right. Look for outliers. What's an outlier? Outlier is defined technically as 1.5 times the interquartile range. I'll define that in a second. An extreme outlier is 3 times the interquartile range. And wild codes. For example, you've got 1 is female, 2 is male in your data, and the 3 pops up there. Oftentimes that comes out of, we purchased our data, for example, from the UFC. You've got data from District Health Council. We have no control over the quality of that data. It's going to have weird things like that. Sometimes the 3 means they refuse to answer, or that data is missing, or something else. Right? So you've got to be really aware of what those numbers mean and be ready to take them out. Okay. These slides just show you where to find. You can do frequencies by looking at SPSS, that stuff. So let's get through that. Okay. The characteristics of your data. There's shape, there's central tendency, and variability. Okay. Central tendency is these 3 things. You know those terms are, right? Mode, median, and mean. Mode is the most common value. Median is the middle value. Mean is the average value. With regression, we focus on the mean. Be aware, though, that if your data is really special, probably isn't, sometimes we'll look at the median. And that requires a bit of a transformation. But in general, we look at means. So here's what it looks like. In perfect data, the mean, median, and mode are exactly the same. And imperfect data, they're kind of skewed that way. Right? So these are measurements of the width of your data. So every variable you have will have one of these measurements for its width. So if it's a continuous variable like age, it's going to have variance, standard deviation, and range. Range is just the difference between the highest and the lowest. Figure out the range of all your variables. If you've got an age range of 0 to 90, let's say, and you've got, and your study is on fertility, you may want to curtail that. You don't need 90 rows of your data, right? That kind of stuff. So range is easy. Interquartile range is harder. It's the hardest one. Interquartile range is the difference between the first quartile and the third quartile. What's a quartile? I'll show you. Let's say these are our data. We've got 11 data points. Let's say it's people's weight. So it's 102 pounds, 104 pounds, 5 pounds, and so forth. I just number the data points here. The middle data point, once I rank my data, is the median. The median is the second quartile. Halfway between the median and the last data point is the third quartile. And halfway between the median and the first data point is the first quartile. Q1, Q2, Q3. The values of those are the quartiles. The interquartile range is that value minus that value. So 115 minus 10. SPSS will do this for you. And you can use that to figure out and let's say you have a value over here, which is 128 or something like that. 128 is significantly greater than 1.5 times the quartile range. So that would be an outlier. Okay. Let me see. Here's an example. So here the weights again, 110 to 190. The interquartile range is 50. How do we get that? Here's our data. What's the middle one? The middle one is here, 150. That's the median. Halfway between here and the first one is going to be here, right? Between 120 and 130. In other words, 125. Halfway between here and there is going to be here. In other words, 175. Okay. So interquartile range is that minus that, which is 50. Again, the computer will do it for you. This is just what it means. Okay. So you can figure that out. Those are okay. Now let's talk briefly about symmetry. Your data can be skewed. So this is a negative skew. Skewness, we talk about the tail. The tail is skewed that way, that's negative. The tail is skewed this way, it's positive. So reversed intuitively. So you don't want skewed data. It can tolerate some skewness, you just don't want extreme skewness. SPSS has a Skewness Index. I forgot what the range is for that one. But if it gives you an extreme skewness number, we'll have to have a conversation what that means.
What would be an example of extreme skewness, like minus 2?
Yeah, I don't remember. I don't remember what the range is. I got to look into that. Yeah, it's not that critical. But if you want to be really anal about the quality of your data, you may want to transform it. And by transform, I mean do a logarithm of it, or something like that. Okay. Right. I don't remember the range of skewness. It was 0 to 1 or whatever it is. But I'm looking at that. So here is some examples of skewness. Okay, other things to look at is kurtosis. Kurtosis is of the flatness redistribution. So here's some fun words you don't need to care about. Leptokurtic, platykurtic, and mesokurtic. Platykurtic, like platypus, means flat. Mesokurtic means in the middle somewhere. And lepto means really thin. So here's an example of a leptokurtic curve. Here's a platykurtic curve, and so forth. And there are indices you can use for that too. Frankly, I've never used that for logistic regression. I don't find it that relevant. Yeah. If this is my curve, it's got a long range, it has a distribution, I don't care. But if we're finding, after we do a diagnosis on your regression, that something's really wrong, we may have to go back and investigate all these things in exquisite detail, just in case. So you sort of see how this is more complicated than it looks at first blush, right? Okay. So, yeah, that's another issue. Oh, good. That's the last slide, really. I don't want to overwhelm you on the first day. So you know where we're going. We're going to create a soup of variables. We're going to prune them and perfect them and get to know them really well. And then we're going to figure out which ones are most relevant for your question. And we define that in two ways. One way is intellectually, like if I'm predicting if a guy's getting elected or not, I don't really care what he had for lunch. That's not going to be strategically a variable, right? I do care, is he an incumbent or not? That's the first way. The second way is mathematically. And this is where the bivariate relationships will come out. So the univariate relationships is the distributions we saw. The bivariates are the independent associations, the odds ratios between each of these unadjusted with the outcome. I showed you how to do one of them using odds ratio. For age, you can't do that. It has to be a different way. You do t-tests and things like that. So I'll plant those things right now with you. And I will upload some sample data. You can play with it, and we'll meet again. So you want to do this once a week? Does that work for you? Or, yeah. Okay, cool. Is that useful?
Yeah,
It is useful.
definitely.
Okay, good. All right, cool. Any questions so far? I can only talk for an hour. Then I get. Okay. Good. Excellent. Excellent. Where's Ideal? Where's Abby? Yes, sir.
Now that I have you here, is it okay if you take a look at my univariate analysis?
Sure. No problem. Let me just stop recording.